This lecture finishes our review of different types of convergence, divergence tests for series. So we've got the ratio test and the root test, and then we'll look back over all of them just a little bit. So with the ratio test, we have a series, sigma a sub n, non-zero terms. They can be positive or negative. It will converge absolutely if when you take a limit as n goes to infinity of the n plus first term over the nth term, it's less than 1. It diverges if you're greater than 1 or infinity. And it's inconclusive if you get 1. And so if it's inconclusive, generally some other tests will work, like a p-series test or a comparison test. So let's take a look at some examples there. So we've got 2 to the nth over n factorial. You do the n plus first term over the nth term. So the n plus first term is 2 to the n plus 1 over n plus 1 factorial, divided by the nth term, so divided by 2 to the nth over n factorial. Let's flip it and multiply. The n factorial, the n plus 1 factorial cancel to an n plus 1. 2 to the n plus 1 and the 2 to the n cancel to a 2. As n goes to infinity, it becomes 2 over infinity, which is 0. 0 is less than 1, so therefore it converges. All right, now we have n squared times 2 to the n plus 1 over 3 to the n. So the n plus first term is n plus 1 squared, 2 to the n plus 2 over 3 to the n plus 1. And then we'll flip it and multiply, so 3 to the n on top, n squared, 2 to the n plus 1 on the bottom. We can cancel all sorts of stuff, and we're left with 2 to the n plus 1 squared over 3 n squared. The 2/3 you can put out front, and n plus 1 squared over n squared goes to 1 squared as n goes to infinity. So you have 2/3 times 1, so 2/3 is less than 1, converges. N to the n over n factorial. Well, you might guess that n to the n is going to, n factorial grows fast, but n to the n grows really, really fast. So this is going to go to infinity, so it's going to diverge. But let's do the ratio test just to conclude that for sure. And so our n plus first term is n plus 1 to the n plus 1 over n plus 1 factorial times the reciprocal n factorial over n to the n. We can cancel the factorials a bit and get n plus 1, and then we can divide n plus 1 off here. So we have n plus 1 to the n over n to the n, which I can rewrite in this way. This limit we've shown before goes to e, and e is about 2.7, which is greater than 1, so therefore it diverges. Here is an alternating series, and so we would want to use an alternating series test to show what happens here, and actually looks like it's going to converge with the alternating series test. But if you tried the ratio test, n plus first term here times the reciprocal of the nth term. Notice we don't have the negative 1 to the n because we're doing absolute values, so we can ignore that stuff. This simplifies down to rad 1 times 1, which is 1, so therefore the ratio test wouldn't help you, it's inconclusive. But you would use a different test to figure this out. So getting to the root test. The root test, again, you have sigma a sub n as your series. It will converge absolutely if when you take the limit as n goes to infinity of the nth root of the absolute value of the series, it's less than 1. Diverges if it's bigger than 1 or infinity. Inconclusive if it's 1. So same conclusions basically as ratio test, but you take an nth root. So this is appropriate in certain situations. This series here, e to the 2n over n to the n. If we take the nth root of this, then it works out much nicer because now we can get rid of these n exponents, and we just get e squared over n. And as n goes to infinity, we have e squared over infinity, which is 0. It's less than 1, so therefore e to the 2n over n to the n will converge absolutely. All right, a few more examples. Here we have n times 2/3 to the n, the ratio test. So limit of the n plus first term over the nth term. And of course, plenty of things cancel. Cancel out these over here. We've got a 2/3 left over, which I'm going to put in front because it's a scalar multiple. Limit as n goes to infinity of n plus 1 over n. As n goes to infinity, this goes to 1. I've got 2/3, which is less than 1, so therefore this will converge absolutely by the ratio test. Here we have 2n factorial over n to the 5th. The n plus first term, after 2n factorial, the next term is actually 2n plus 2 factorial. That's because if you put in n plus 1 for n, and n plus first term, you distribute the 2 and get 2n plus 2 factorial, n plus 1 to the 5th, and then times the reciprocal, n to the 5th over 2n factorial. Plenty of things cancel. From the factorial, we're left with 2n plus 2 times 2n plus 1, and then n to the 5th over n plus 1 to the 5th. And we can put these together. And as n goes to infinity, this is going to go to infinity because this will be 1 to the 5th, but this will be infinity. So infinity, of course, is too big, and so therefore we're going to diverge by the ratio test. Another ratio test example, n plus first term after 2n is again 2n plus 2. After 3n minus 1 is 3n plus 2 because you're adding 3 to 3n minus 1 because remember you're distributing a 3. And then times the reciprocal. And again, plenty of things cancel out, so all of this cancels. And all of this cancels. And we're not left with very much. All we have is 2n plus 2 over 3n plus 2, which goes to 2/3 as n goes to infinity. It's less than 1, so therefore it converges by the ratio test. And then let's look at one more example involving root test. We have 2 to the nth root of n plus 1 to the nth power. So we will take the nth root of all of this. That cancels out this power. So now I just have this part in here. Now, we already know this is going to go to 1. So there's no way this is going to converge because it's either going to be 0 plus 1, which will be inconclusive, or a positive number plus 1, which will diverge. But let's find out what this part is equal to. So we'll make a little variable substitution. We're going to put the 2 out front first of all, scalar multiple, and we'll call this limit here, we'll call that y. So where y is equal to the limit as n goes to infinity of the nth root of n. And now let's just figure out what this one piece is, and we can go back and figure out what happens with the whole series. So what we do is we rewrite as n to the 1 over n. And this is infinity to the 0 power, so that's indeterminate. So what I will do is take a natural log of both sides. And in doing the natural log, I can take the exponent and put it down in front as a coefficient. And now we have 1 over infinity, which is 0. Ln infinity is infinity. So now it's, again, indeterminate. But what we can do is write it as a fraction. So ln y is now going to be ln n over n. So now we have infinity over infinity, which allows me to then use L'Hopital's rule. We'll take the derivative of the top and the bottom. So derivative of ln n is 1 over n. Derivative of n is 1. Plug in infinity and you get 0. So ln y is equal to 0. So therefore y is e to the 0. So now we finally have y as 1. I would go and plug it back up top. So we'll do that. So that limit was equal to 1. So therefore, this expression here is 2 times 1 plus 1, which is obviously bigger than 1. So therefore, the original series diverges by the root test.